All right. Good morning, everyone. My name is Caitlin Kruger, and I'll be your tutor for today in mathematics. Today we are going to look at trig reduction. So most of you would have done this in your term one. I'm going to go over kind of the beginnings of trig reduction, where it comes from, and then we'll do some examples, and hopefully it'll cement it for you and it'll make a whole lot more sense. So from grade 10, you would have learned sine of theta is equal to y over r when we're looking in the Cartesian plane. We've got cos of theta, which is x over r, and we've got tan of theta, which is equal to y over x. So if you've got your Cartesian plane, which I have over here, if you've got an angle theta measuring from the x-axis anti-clockwise, and your point x, y, the distance from the origin to that point we call r, and using our different trig functions, we can find sine of theta by taking the y value over r, cos and tan. So that was your grade 10 work, and we only worked within the first quadrant of the Cartesian plane. Remember, our second quadrant is over here, third quadrant over here, and fourth quadrant over here. So in grade 11, we start to look at what happens when we move into quadrant 2, quadrant 3, and quadrant 4. So if I were to reflect this line, this blue line I've called R, over the y-axis, we end up with something, we end up with a line that looks like this in our quadrant 3. And if we're reflecting over the y-axis, what happens is my x value changes sign. I'm in the negative x quadrant, but my y value is still the same. My r value is still the same. And this angle over here is now the angle theta. So if I'm measuring from the positive x-axis anti-clockwise, this full angle here, this obtuse angle, is 180 degrees minus theta. So we're in quadrant 1 and we're looking at angles where we have 180 degrees minus theta. Now we know from grade 10 that sine of our angle is going to be the y coordinate over the r coordinate. So our y coordinate in this quadrant over here is just y, but our x coordinate has changed sign, but we're looking at sine, so y over r, which is exactly the same as what we had if we just looked at sine of theta. So that's our first reduction formula that we get. Sine of 180 minus theta is equal to sine of theta. But if we were to look at, say, cos, in the second quadrant, cos of 180 degrees minus theta, cos is x over r. But now in quadrant 2, my x is now a negative x. And so we end up with a negative cos of theta. It's changed sign when we're in quadrant 2. And our tan, if we look at tan in quadrant 2 of 180 degrees minus theta, tan is y over x, so it will be y over negative x in this quadrant 2. And so once again, we get negative tan of theta. All right, so those are our reduction formulae for quadrant 1. Sine of 180 minus theta is equal to sine of theta. So there's been no sign change. But cos of 180 minus theta is now negative cos of theta. Tan of 180 minus is also negative tan of theta. So those are our 3 from quadrant 1. I'm going to go through quadrants 3 and 4 quickly. Right, let me just redraw that Cartesian plane. So remember, we started off with this line here, xy, in our quadrant 1, and the theta was the angle that we were dealing with there. So if I now move this line and I move it to quadrant 3, this angle from the positive x-axis all the way down there is now 180 degrees plus theta. So we're looking in quadrant 3 of our Cartesian plane. And what happens with our x coordinate is it is now a negative x coordinate, and our y coordinate, because we're below the x-axis, is also a negative y. So if we go back to our sine, cos, and tan, we can now see in the third quadrant what happens if I've got sine 180 degrees plus theta. Well, we know sine is y over r, so we're going to get negative y over r. Remember, r is the distance from the origin to the point, and it is always positive. So by seeing this, we see we've got a negative y over r, which is negative sine of theta, which we had at the beginning. So in quadrant 3, sine of 180 plus theta is equal to negative sine of theta. If we look at cos we know from grade 10 is x over r. In quadrant 3, our x value is negative. And so we see that we've got negative cos of theta in quadrant 3. And our tan of 180 degrees plus theta is going to be, tan is y over r, so we get, y over x, so we get negative y over negative x, because we're now in quadrant 3, which simplifies to y over x, which is exactly what we got in quadrant 1, tan theta. So notice here in quadrant 3 that we're looking at, the sine is negative, cos is negative, and tan is negative. All right, let's move on to quadrant 4. Hopefully this is all ringing a bell because you would have done this already. If we're sitting in quadrant 4, so there's our original XY line and the angle theta. If I now move into quadrant 4, what I've done is I've reflected over the x-axis. So now my x value is still positive, but my y value is negative. We're below the x-axis. Remember, we measure angles from the positive x-axis anti-clockwise to there. Or you could have thought of this angle as 360 degrees minus theta. 360 degrees would be going the whole way around. Let me just change my color so we can see. 360 would be going all the way up there and then taking away theta. So we're dealing with 360 degrees minus theta when we are in quadrant 4 of our Cartesian plane. So if we go to sine, cos, and tan, like we have for all the quadrants, sine of 360 degrees minus theta, we're in this quadrant 4, sine is y over r, and my y value is now negative in this quadrant. Okay, remember the r value is still the same from the origin to the point. So negative y over r is negative sine of theta, what we got in the first quadrant. We can look at cos of 360 minus theta, and cos is x over r. So in our case, x is still positive and r is also positive. And so we end up with exactly what we got in quadrant 1. And tan of 360 minus theta, we're sitting here with y over x, and y is now negative. And so we see we've got a negative what we got in the first quadrant. So in quadrant 4, we see that sine and tan are negative while cos is positive. And so we end up with our reduction formulae. Now, the easiest way to remember your reduction formulae is to remember the cast diagram. So what we saw in quadrant 1, I'm going to recap it here for you, was that, cos of theta is x over r, sine of theta is y over r, and tan of theta is y over x. So all my ratios are positive in quadrant 1. So when we're dealing with our quadrant 1, I'm going to say A for all being positive. When we got into quadrant 2, now in quadrant 2, remember we dealt with 180 degrees minus theta. That would give me angles in quadrant 2. And we saw that sine of 180 degrees minus theta was equal to sine of theta, what I discussed on that first slide. So I'm just summarizing it here for you. Cos of 180 degrees minus theta was negative cos of theta, and tan of 180 degrees minus theta was negative tan of theta. So what we can see in quadrant 2 is the only one that is positive is sine of theta. So in our cast diagram, I'm going to put an S to remind me that sine is the only one that's positive in this quadrant. Quadrant 3, we deal with 180 degrees plus theta. Remember, that's how we get to angles in quadrant 3. And as a recap, what we ended up with in that third slide, I think it was, that I shared with you, sine of 180 plus theta gave me a negative sine of theta. Cos of 180 degrees plus theta gave me a negative cos of theta. And tan of 180 degrees plus theta gives me a positive tan of theta. So from here, we can see in quadrant 3, the only positive ratio is tan. So if we're dealing with quadrant 3, I'm going to write, a T for tan. How do I erase? Right, and then we looked at quadrant 4 briefly on the last slide. We said to get to angles in quadrant 4, we say 360 degrees minus theta would give me an angle in quadrant 4. And we saw that sine of 360 degrees minus theta was negative sine of theta. We saw that cos of 360 degrees minus theta was positive cos of theta. And we saw that tan of 360 degrees minus theta was negative tan of theta. So the only positive one in this quadrant is cos, which is why we write C over there. So this is our cast diagram, which I'm sure you're all familiar with. And the really useful thing about it is that we don't have to remember all of these different formulae. We don't have to remember all 9 of them. We can just remember the cast diagram, and then we know whether it's going to be positive or negative. You can add to your cast diagram the angles, just to remind you. So in quadrant 1, we speak about angle theta, or some acute angle. In quadrant 2, we said 180 degrees minus theta. In angle 3, it was 180 degrees plus theta. And in quadrant 4, it was 360 degrees minus theta. If you can remember this cast diagram, then you're good to go for any trig reduction. It summarizes it for you, and everything is a whole lot easier. All right, I'm going to do an example using these 4 quadrants. There's more to trig reduction, but we'll get there. So let's do some examples on this. All right, so our question is simplify fully. All right, sometimes they'll say reduce to a trig function of an acute angle. The first question here we have is sine 180 degrees minus theta. Now this is a basic one, we've just talked about it, but the way you would go through answering a question like this is by first drawing a little cast diagram for yourself. Okay, remember we start with C in quadrant 4. Then we have to identify which quadrant this angle is talking about. So an angle of 180 degrees minus theta is talking about quadrant 2 in our cast diagram. So if we go to quadrant 2, we see that sine is positive, okay, and everything else would be negative. Our function that we've got, or our trig ratio, is sine. So it is going to be positive sine, and we reduce it to the acute angle, positive sine of theta. So we identify the quadrant, then we identify whether it is positive or negative. We could have a look at a question like sine of 290 degrees. So this is now a numerical example, sine of 290 degrees. So I would have to identify in which quadrant we're looking at. So it's greater than 180 degrees, but it's less than 270 degrees. So this tells me we're in quadrant 3 in our Cartesian plane. Right? Remember, 180 degrees is your horizontal line, and this would be at 270 degrees. Sorry, so I've made a mistake here. We are actually in quadrant 4 because we are past this 270 degree line. So our angle's sitting somewhere down here, going all the way from 0 to 270 degrees. So it's not in quadrant 3, it's actually in quadrant 4. So if we look at our cast diagram in quadrant 4, we see that cos is the only positive ratio in quadrant 4. And we're talking about sine. So we know that the answer is going to be negative. But let's first rewrite this as an angle in quadrant 4. So angles in quadrant 4, we want to rewrite as 360 degrees minus something. So if we take our 290, we can work out that it's 360 degrees minus 70. That gives me exactly this 290 degrees that we're talking about. So 290, we've rewritten it as 360 minus 70, right? And so now we can use our reduction formulae. We know we're in quadrant 4. We know that means sine is negative. So we reduce it to negative and then sine of the acute angle that we worked out over here. All right, so that's how you would go about doing these basic type of reduction questions. You identify your quadrant, you rewrite your angle as per the quadrant, and then you use your cast diagram to decide whether it's going to be positive or negative. Now, in this last slide, let me just go back. We dealt with 180 minus, 180 plus, and 360 minus. You've all done it before, so I'm sure you know there's an angle of negative theta as well, and 360 plus. So we're going to look at that, negative and 360 plus. All right, so if I go and look at a negative angle, negative theta, what a negative angle means is that we have changed direction. We are measuring in a clockwise direction. Normally measuring in a clockwise direction. Normally we would be measuring anti-clockwise as we go along our Cartesian plane. So if we measure in a clockwise direction, an angle of negative theta will bring us into quadrant 4. And the same rules apply. If we are in a negative theta quadrant 4, our x value will be positive and our y value will be negative. Our r value is always positive. So it works exactly the same as our 360 degrees minus did. So I'm going to just go back to that 360 degrees minus slide over here. We saw that sine of 360 minus was negative sine, cos was positive, and tan was negative. Because we're in the same quadrant, it's going to work the same. So if we're here in quadrant 4, because we've got a negative theta, our reduction formulae is sine of negative theta. Let's just go through it slowly, is negative y over r, which is negative sine of theta. If we look at cos of negative theta, cos is x over r, and we have a positive x and a positive r, so it's the same as positive cos of theta. And if we look at tan of negative theta, Tan is y over r. And we end up with a negative tan of theta. So the same rule applies. The only one that is positive is cos of theta. All right, so you can add that to your cast diagram. If we go back here, your cast diagram, this quadrant 4 is not only 360 minus, but it's also negative theta angles as well. Give you exactly the same results in quadrant 4. All right, we're going to look at multiples of 360 as well, or adding multiples of 360. So if you look at 360 degrees on your Cartesian plane, right? Now we're going back to positive angles. 360 degrees would mean we've gone all the way around and we're back to where we started. So if I talk about an angle of theta plus 360 degrees, we would say, right, theta may have been in the first quadrant. That is my angle theta. But if I'm saying 360 degrees plus theta, it means I'm taking the theta and I'm going 360 degrees all the way around and back to where I started. And if I had theta plus 720, 720 is just 360 degrees plus 360 degrees. And so that would be like going around twice, 360 and then 360 degrees again. And we always end back where we started. Even if we had started in some other quadrant over here, if we had our angle and then we added 360 to that angle, we would end up in exactly the same position as we did when we started. So when you have 360 plus, you can just reduce them to the acute angle. So if I have sine of 360 degrees plus theta, it's exactly the same as sine of theta. If I have cos of 360 degrees plus theta, it's exactly the same as cos of theta. And if I have tan of 360 degrees plus theta, it's exactly the same as tan of theta. So it just brings it back right where we started and nothing changes. It works for any multiples of 360 as well. So this example here, I talked about 720. You could have had 3 times 360, so 1080 would work exactly the same because it just brings us back right to where we started. Okay, what I've discussed is our normal reduction. There's still the co-ratios that we're going to talk about. But if any of you have a question and would like me to go back over something before we do some examples, you can let me know. Otherwise, we're going to just continue and do some examples with this reduction so far. Okay, give me a second. I'm just going to add a few more slides if I can. Okay, and we should be good to go. All right, so let's just do 1 or 2 examples on what we've discussed so far. So our question is, simplify the following to a trig ratio of an acute angle. So whenever we're doing reduction, we are wanting to reduce as far as possible to an angle that's between 0 degrees and 90 degrees. All right, so if we look at our first example, cos of 765 degrees, our steps are the same. We are trying to decide in which quadrant we are, but 765 is bigger than 360. So we can rewrite this as 360 degrees plus something, because it's greater than 360 degrees. So 765 is 360 degrees plus 405 degrees. And what we discussed just now is we said that cos of 360 plus anything just reduces to cos of the angle. We're back where we started. So I could reduce this to cos of 405 degrees. But that's still greater than 360 degrees. So I can rewrite it as 360 degrees plus something again. And we can work out that 405 degrees is cos of 360 plus 45 degrees. And so once again, I can reduce this to cos of 45 degrees. And that is my final answer. I now have an acute angle. I didn't have to change it to negative or anything like that. And I have my answer. You really could have gone straight to the answer. There's no need to write all these steps, but these steps explain kind of where it comes from, this cos 360 plus idea. Okay, let's look at a second example. Tan of 720 degrees minus theta. Okay, so 720 degrees minus, that's not one of our normal diagram or cos diagram angles that we get. Remember, our cos angles, or sorry, our cos diagrams tell us 180 minus, 180 plus, and 360 minus. So if we have 720 minus, what is that? Ah, thank you. Not used to the time. All right, so let's just quickly go through this, this one here. 720 is not an angle we're used to, so we can subtract 360 from it. Remember, every 360 degrees, we're back where we started. And so now I'm in quadrant 4. So if I go to my cos diagram, in quadrant 4, we know that cos is positive and everything else is negative. And so we get negative tan of theta as our answer. All right, we are running short of time, but I do want to quickly go over your co-ratios and then end with 1 or 2 examples. So I'm not going to go over the full derivation of where they come from, but we're just going to talk about how you would use your cos diagram to get there. So your co-ratios are 90 degrees plus and 90 degrees minus. Let's start with the 90 degrees minus theta. If I look at a cos diagram, 90 degrees is sitting up here. So 90 degrees minus is going to give me an angle in the first quadrant. And my cast diagram tells me that everything is positive in this quadrant. So I can have sine of 90 degrees minus theta, or I can have cos of 90 degrees minus theta. Right, and we know with our co-ratios, they swap from being sine to cos or from being cos to sine. But what is important is that we're in quadrant 1, and so there's no sign changes. We don't have negatives popping up. If we look at our 90 degrees plus though, 90 plus means we are now in quadrant 2. I'm going to do it with red. And so it tells me that sine is the positive one. So if I have sine of 90 degrees plus, sine is positive in quadrant 2. Because it's a 90, it swaps to a cos. But if I had cos of 90 degrees plus theta, cos is negative in quadrant 2. And so it becomes negative sine of theta. And that's the really easy way to remember using our cast diagram. So we've gone through 180 minus, 180 plus, 360 minus, and now we've looked at our 90 plus and 90 minus co-ratios. They are co-ratios because whenever we've got our 90 degrees plus or 90 degrees minus, we end up changing it from a sine to a cos or the other way around. Here we had 90 plus, and once again, we're changing from sine to cos. There are no tan co-ratios, just the sine and the cos. All right, we are going to hopefully bring this all together with an example that kind of encompasses everything. Okay, so our example is to write everything in terms of a single trig ratio if we can. So cos, sorry, let me change this quick. We've got sine of an angle minus 180 degrees multiplied by tan of negative the angle minus 180 degrees multiplied by cos 180 degrees plus the angle all over cos of negative the angle times sine of 360 plus the angle. As I go through this one, try and do it with me. See if you can get to the reduction before we do. So if we look here, sine of beta minus 180, that is not one of the angles in our cast diagram. We have 180 minus, 180 plus, or 360 minus. So beta minus 180, it's written in the wrong way. I'd like to rewrite this as 180 minus beta. But I can't just do that. I have to do a change of sign rule. So I've taken out a negative. Right, the same with this next one. Minus beta minus 180. That's not one of our angles. But if I take out a negative, I end up with a positive 180 plus angle beta. And cos 180 plus beta is fine. It can stay like that. If I look in our denominator, we've got cos of negative beta and sine of 360 plus beta. We can leave it like that, or you could have done your reduction at this stage. Now that our angles are all looking good, let's start at the top. Sine of negative something. Okay, so we're going to treat this angle as this bracket as our angle. Sine of negative theta. Let's think about where negative gives, where we end up if we're doing negative. That would be in quadrant 4. Sorry, the pen color, let's change it. So it would be in quadrant 4 because we've got negative angles. And our cast diagram tells us in quadrant 4, cos is the only positive one. So this will reduce to negative sine of 180 degrees minus beta. Tan of a negative, that's also quadrant 4, and it's going to be negative tan of our angle. Cos of 180 plus, that is quadrant 3. And we know that tan is the only positive one, so that is going to give me a negative cos of beta. In my denominator, cos of negative beta, that negative beta is in quadrant 4 and cos is positive, so we get cos of beta. Sine of 360 plus, that's like just having beta, add 360, we're back where we are, so it is just sine of beta. So I've done my first round of reductions. Please make sure that your multiplication dots are clear. Your other option is to put big brackets around these factors. Right, we've got 2 more steps. If we look at this first term, sine of 180 minus, that is in quadrant 2, and we see that sine is positive. So the negative is from the question, but this second part just stays as sine of beta. Then 180 plus, that is in quadrant 3, and we see that tan is positive. So once again, the negative is from the previous step, but it reduces to a positive tan of beta. And we're multiplying by a negative cos of beta all over cos of beta multiplied with sine of beta. So now all our angles are reduced to beta. So I can start to multiply and simplify. We can see in the numerator, we've got a negative times a negative times a negative. So I know my final answer is going to be negative. And then everything is being multiplied. So I'm allowed to cancel out my terms. So I can cancel out sine beta from the top and the bottom, and I can cancel out cos beta from the top and the bottom. And so my final answer is just negative tan of beta. And that is my final answer. I've used reduction, and I've come up with an answer that is as simplified as possible. All right, so each step along the way, identify which quadrant you're in, identify whether it's positive or negative, and then you can go and reduce your angles completely. Okay, we've got about 10 minutes left, I think. So there's time for us to do another example, but I just want to make sure everyone's happy. If you have any questions, let me know. But otherwise, we will continue with another example. Your cast diagram is the biggest tool you have on hand when you are doing these questions. It summarizes all of reduction at once and makes your life a whole lot easier. So I suggest that every time you do one of these questions, you draw up your cast diagram if you struggle with this section especially, and then you can go from there. All right, our last example is going to include a little bit of identities. Now, I haven't discussed identities, but you will have done this in class, so it can be a little recap of its own. This is our question, and we are asked to simplify it as far as possible. Now, the first thing I notice is that there are 4 different angles happening here. We've got 140, 40, 220, and 50. So let's just start by reducing everything we can to acute angles. 140 degrees. That is in quadrant 2. Okay, my cast diagram is up on the side. 180 minus is how we want to write things in quadrant 2. So this first step that I've got here, I'm going to rewrite this as 180 degrees minus 40, because 180 degrees minus 40 is the same as 40. All right, tan squared 40, it already is an acute angle, so I'm going to leave it like that. Cos of 220. 220 degrees is in quadrant 3. And quadrant 3 angles we want to write as 180 plus. So 220 degrees is 180 degrees plus 40. All right, so let's use our reduction. Cos squared of 180 degrees minus 40. We're on quadrant 2, so this is going to give me a negative cos 40. But it's being squared. So if you want to see it like this, negative cos 40, remember cos squared means we are taking this answer, this cos 40, and we are squaring the whole thing. Minus tan squared 40. Once again, we're in quadrant 3, cos 180 plus, and that is going to give me a negative cos of 40, because tan is the only positive one in quadrant 3. All right, so if I square something that's negative, I just end up with a positive answer. So we can reduce this to cos squared of 40 minus, I'm actually going to write it as a plus if we're looking at our negative times by a negative, so that gives me plus, and then we've got tan squared 40. We've got cos 40, and now we've got this sine of 50. Now, every other angle is working for us except for sine of 50. So let's take this and try and make it into an angle of 40. And what we can see is that this is the same as 90 degrees minus 40 degrees. Okay, and that is our co-ratio coming into it. So we've got cos squared 40 plus tan squared 40 times cos 40. Sine of 90 minus, remember, brings us back into quadrant 1. So it's going to be positive, but it changes to a cos because it is a 90. It's a co-ratio. So what we've got here is cos squared 40 plus tan squared 40. Cos 40 times cos 40 is cos squared 40. And so now we can see, we can start to factorize, maybe, to simplify this a little bit. Cos squared 40 and cos squared 40 appear in both of our terms. And we could simplify our answer like that. Right. I'm actually not going to simplify it, sorry, like that. What I'm going to do in this previous step, because we can actually simplify our answer a little bit further. If you're remembering your identities, tan is sine over cos. So what I'm going to do is I'm going to, instead of factorizing, I'm going to write this as sine squared 40 over cos squared 40. So that's your tan identity coming into it. And that is going to allow me to simplify even further. So what we used there was the fact that tan of an angle is sine of your angle over cos of an angle. So if I look now, I've got a fraction multiplied by cos squared 40. So this cos squared 40 and this cos squared 40 will cancel out, which is great because now I'm getting more simplified. So what I've got is cos squared 40 plus sine squared 40, and that is another identity. If you remember, sine squared of an angle plus cos squared of an angle is always equal to 1. So now it's irrelevant that my angle is 40 degrees. I know that if I add cos squared and sine squared together, if the angle is the same, I end up with 1 as my answer. So this whole long thing with a whole bunch of different angles has reduced to a single value. It's just equal to 1. So remember, with your trig, you've got your reduction, you've got your co-ratios. You also have to remember you've got algebraic fractions and remember how they work. And you've got these identities as well. All right. I'm not going to go any further. We do have a few minutes left, but that's it for today. We've recapped our reduction and we've recapped a little bit of identities as well. This helped you revise and remember a little bit of your trig reduction from this year. But that is it from me today.